Okay, welcome back. So in the first part of today's video, we talked about functions of two or more variables, and I ended that particular section by asking the question of if we change the number of units produced and sold, if we increase, in other words, if we increase the number of units produced and sold, how does that change the profit? And that's a question that we've actually already asked during this semester. We've asked the question of what is the rate of change of profit? What is the rate of change of cost? The rate of change of revenue? And when we talk about a rate of change, what we're actually talking about is the derivative. And so this idea of asking about change, and that corresponds to the idea of a derivative, we've talked a lot about that earlier in the semester. When it comes to functions of two or more variables, we need to tweak this just a little bit. When we have a function of more than one variable, so for functions of more than one variable, instead of having a derivative, we have something called a partial derivative. And we have a partial derivative associated to each of the input variables. So for functions of more than one variable, we have things called partial derivatives. And that's what we're going to talk about during this section of our class. Today I'm going to talk about what a partial derivative is, how to calculate one, the notation that we use for them. But what I'm not going to talk about is I'm not going to talk a lot about interpreting the meaning behind a partial derivative. That will be our class on Tuesday. And that'll be our final day of new material, by the way. So today we're going to talk about what a partial derivative is, the notation, and how to calculate a partial derivative. Okay, so let's start with some notation. So typically we have a function, and now that we're talking about a function of two variables, now I have two inputs inside the parentheses. So our function name is f of xy. And then we have the partial derivative. And we will have a partial derivative for each of the input variables. So we have a partial derivative with respect to x and a partial derivative with respect to y. So partial derivative with respect to x, and f with a subscript y is our partial derivative with respect to y. And you might be saying, well, wait a second, Diane, time out. When we talked about functions of one variable, when we talked about something like the function f of x, then our corresponding derivative notation was a prime. We put a prime up next to the f, and so it was f prime of x. The difference now is that we actually have to clarify or specify whether we're talking about with respect to the first variable x or the second variable y. So I can't just put a prime, I actually have to put the variable that I'm talking about there. And since I'm going to put those as subscripts, I don't bother to put the prime at the top. Okay, so our partial derivatives are fx and fy. Now, like we had with one variable functions, sometimes we named the function y, and then our derivative would be dy over dx. So that was that Leibniz notation that we sometimes used. Okay, we have something similar for partial derivatives, and so the way we write this, and I'm going to write it down and then we'll talk about what it means. This notation that I've written down here, it looks like I have a backwards 6 and then an f over a backwards 6 and then an x. That backwards 6, that's our partial. So we say the partial derivative of f with respect to x. df over dx is how we read it, but it uses these funny looking, backwards looking 6, almost like a 2 with the tail cut off. Okay, so that's our partial derivative of f with respect to x, and we have our partial derivative of f with respect to y. And just like with regular derivatives, you want to be comfortable with both the subscript notation and also, this is called our Leibniz notation. Okay, so now that we've seen this notation, let's calculate some partial derivatives. And again, I want to emphasize that today we are not going to talk about what these partial derivatives tell us or how we want to interpret them. That's our class on Tuesday. Today we're just talking about the how-to part of calculating these derivatives. Okay, so our example, we have the function f of xy is equal to 3x squared minus 4y plus 12x squared y minus x cubed y squared plus 14. All right, and our instructions are to find the partial derivative of f with respect to x and the partial derivative of f with respect to y. And again, you don't necessarily ever have to write the notation with this funny backwards looking d, but you can. But what you do want to be comfortable with is when you see that notation of partial of f with respect to x, that this is the same as f subscript x. And this partial derivative with respect to y is the same as f subscript y. You can choose whichever notation you want to use. Okay, so let's start with our partial derivative of f with respect to x. Okay. And so we want to think about how we're going to calculate this partial derivative. And the thing I want to look at is I want to look at the variable that's in the denominator. In this case, that's an x. And what I want to think about is I want to think of x, that's the letter in the bottom, as the only variable in this function. So we want to think of x as the only variable, and we want to think of, well, the other variables that are in there is the y. So we have x's and we have y's. X will be our only variable, and we want to think of y as a number. Okay. The idea is when a term has an x in it, then we carry along all the numbers or constants and take the derivative of the x portion of the term. Okay, so that's a lot of words. Let's look at an example. Okay, so our function is f, and by the way, I'm going to get a little lazy and I'm going to stop writing the f of xy and I'm just going to call this guy f. And so our function that we wrote down is 3x squared minus 4y plus 12x squared y minus x cubed y squared plus 14. And we want to calculate the partial derivative with respect to x. So I'm thinking about x as the variable. So x is a variable and y is going to be a number. All right, so looking at what I have written up here, I'm going to identify the terms that are strictly numbers. So 14, this is just a number. So when I get to that one and I take the derivative of 14, my derivative will be 0. This 4y, that's also just a number. So even though there's a y in there, anytime that I see a y, I want to look at that y and say, you know what? You're a number. You're not a letter, you're a number. You're a funny looking number, but you're a number. Okay? So when I take the derivative of 4y, there are no x's in that term. That is just a number sitting by itself, so its derivative will be 0. Okay, now on the other hand, we have a couple of terms that involve x's. We have the 3x squared, the 12x squared y, and the x cubed y squared. On this first term, the part that has the x is the x squared. In the 12x squared y, the part with the x is also an x squared. And in the x cubed y squared, the part with the x is x to the third. Okay, so we're going to take our partial derivative of f with respect to x. I can use the subscript x notation, or I can write partial of f with respect to x. It does not matter. All right, so 3x squared. According to my instructions, when a term has an x, we're going to carry along all of the numbers or constants and take the derivative of the x portion. So for 3x squared, I'm going to carry along the 3, and I'm going to take the derivative of x squared. So I have 3 times 2x. Okay. Now I have a minus sign. This 4y, no x is involved whatsoever, so we think of that 4y as a number. Its derivative is 0. And then I have a plus sign. Looking at this next term, I've got the 12 and the y. I'm going to carry those along, and I'm going to take the derivative of the x squared. So I carry along the 12. Derivative of x squared is 2x, and I carry along the y. Write down the minus sign. Take the derivative of the x to the third, which is 3x squared. Carry along the y squared. And my derivative of 14 is 0. Okay, so my final step on calculating my partial derivative of f with respect to x is to clean up. So 3 times 2x is 6x, minus 0, I don't have to write that. 12 times 2 is 24, so I have plus 24 times x times y, minus 3x squared y squared. And there is my partial derivative with respect to x. Okay, so now we're ready to find the partial derivative of f with respect to y. And so we're gonna have a very similar process to our partial derivative with respect to x. And I would encourage you to maybe even pause the video and look at the steps or the statements I made about the partial derivative with respect to x, and see if you can kind of rearrange those and see if it'll match up with what I'm about to say. Okay, so to find the partial derivative of f with respect to y, or f subscript y, fy, the first thing we want to do is we want to identify that subscript letter, or that letter that's in the denominator. In this case, that's a y. And so the first thing we want to do is we want to think of y as our only variable. And any other input variable that we have, in our example up here, our input variables are x and y. We want to think about any of those other input variables, in this case x. We want to think of x as a number or as a constant. And once you kind of get that mindset, and for me, I always pause at the beginning of one of these problems and say, okay, y is my variable, x is a number. And once I do that, then when a term has a y as part of the term, we carry along the numbers and the constants, take the derivative of the y part of the function. Okay, so let's look at it for our specific example. Our function is f equals 3x squared minus 4y plus 12x squared y minus x cubed y squared plus 14. Okay. And we want to find the partial derivative with respect to y. So I want to think about y as being our variable and x is a number. And I really do write that down every time I do one of these problems, because if you mix that up, then everything gets wrong. Okay, so y is our variable and x is a number. So when I look up, let's see, I need purple. When I look up here, x is a number. So this 3x squared, that entire term right there is a number. This next guy involves a y, the next guy involves a y, the next guy involves a y, and then the 14 does not involve a y, so 14 is just a number sitting by itself. So the terms where there is no y involved whatsoever, the derivative will be 0. Now, for the other terms, the 4y, the 12x squared y, and the x cubed y squared, the portion that has the y in the 4y, the portion is just a y. 12x squared y, the portion that we're going to take the derivative of is the y. And in the x cubed y squared, we'll take the derivative of the y squared part. Okay, so our partial derivative of f with respect to y, the derivative of a number sitting by itself, and even though there's an x in there, I'm looking at that x with special glasses on that say that x is a number, so its derivative is 0. Then I have a minus sign. And for this term that involves a y, I will carry along any number that's associated with that term. So I have the 4, and the derivative of y will be 1. Then I have a plus sign. For the 12x squared times y, I carry along the number portion, that's the 12x squared, and I take the derivative of the y part, and the derivative of a y by itself is 1. Then I have a minus sign. And for the x cubed y squared, the x cubed is my number part, so I'll carry that along. X cubed, I'll take the derivative of y squared, means I bring the 2 down in front, so I have 2y. And then I have plus the derivative of a number by itself is 0. So now I've taken the partial derivative with respect to y, and now I want to clean things up. So I don't need to write the 0. So I have negative 4. 12 times 1 is 12. So I have negative 4 plus 12x squared minus, and then for this term right here, it's customary to put the number in the front and then have your x's to a power and then your y's to a power. So I'm going to reorganize this as 2x to the third y, and I don't need to write the plus 0 at the end. Okay, so this is our partial derivative with respect to y. So the good news is that when we talked about derivatives, we learned rules like the product rule, the quotient rule, the chain rule, derivatives for natural log, derivatives for exponential functions, all of those things we talked about with functions of one variable. You can do all of those rules with partial derivatives. The good news is that we actually only spend a day or a day and a half on partial derivatives, so we're not going to go into the depth of all of those rules for derivatives. We're going to stick with pretty much the power rule. And so that's the good news. The bad, or maybe it's not bad, but interesting news is that now, instead of finding a derivative, if you have a function of two variables, like this one up here that's in terms of x's and y's, that means now you have two partial derivatives. If you had a function with 3 input variables, you would have 3 partial derivatives to calculate. So our work is getting more work, but we're not going to get as in-depth with it. Okay, let's look at a couple of more examples. that whining, that was Aquila, and now she's running away, and there goes Franklin. Oh, and we have all three of them together now. 2 hiding, about ready to fight, and 1 up on the air hockey table. All right, and we're back. Okay, so our example is P of xy is equal to 10x plus 6.4y minus 0.001 x squared minus 0.025 y squared. And this might look familiar to you. In part 1, this was our example of the joint profit function, where x represented the number of pounds of kisses and y represents the number of pounds of cream. And this formula tells us the total profit for x pounds of kisses and y pounds of cream. Okay, so in this example, what we're going to be doing is we are going to find the partial derivative of p with respect to x and the partial derivative of p with respect to y. So we'll start with the partial derivative of p with respect to x, and as soon as I write that down, I immediately want to think, okay, x is in my denominator, so x is my variable and y is a number. Okay, so I like to start by writing down the original function. So p is 10x plus 6.4y minus 0.001 x squared minus 0.025 y squared. So our partial derivative of p with respect to x, when I look at this first term, so x is our variable and y is a number. So in this first term, I see an x, so I'm going to carry along the number, the 10, take the derivative of the x, which is 1. My next term, 6.4y, there are no x's whatsoever, so this entire term is a number, so its derivative is 0. My next term, I have a number times something involving an x, so I'll carry along the number and take the derivative of the x squared, so the derivative of x squared is 2x. And then our last term, the 0.025 y squared, there are no x's involved whatsoever, so this entire term we think of as a number sitting by itself, so its derivative is 0. So once I write all of this stuff down, I can simplify. 10 times 1 is 10. I don't need to write the 0. 2 times 0.001 is 0.002x minus 0. So our partial derivative of p with respect to x is 10 minus 0.002x. Now, as you start doing more of these partial derivatives, when you start doing 5 of them or 10 of them or 20 of them, then you may not necessarily write this intermediate step. You might go ahead, and say, oh, I can bring that 2 down and multiply it in the front. And that's totally fine. But I would recommend, at least for the first few of these practice examples that you write out that intermediate step. Okay, so that's our partial derivative with respect to x, and we also want to find the partial derivative with respect to y. Partial derivative of p with respect to y. I now want to reset my mind, and now I want to think that y is my variable and x is a number. Okay, so I start by writing down my original function, which is 10x plus 6.4y minus 0.001 x squared minus 0.025 y squared. And now I'm ready to find the partial derivative of p with respect to y. So my first term, there's no y whatsoever. So in this first term, the entire term is a number, so its derivative is 0. My next term involves a y, so I'll carry along the number, 6.4, take the derivative of y, which is 1. Then I have a minus sign. my next term does not involve any y's. So my next term, the 0.001x squared, is a number sitting by itself. Its derivative is 0. And finally, I carry along this number, 0.025, and take the derivative of y squared, which is 2y. And once I've written all of this down, I can clean up. And so my partial derivative of p with respect to y will be 6.4 minus, okay, and then 2 times 0.025 will be 0.05 y. So we have our partial derivative with respect to x, our partial derivative with respect to y. One question that you might be thinking right now is, that's great, I can do this, but what do these things tell us? Wait until next class for that one. The other question that you might have is, Diane, this second example felt a little easier than the first example. Why is that? And part of that reason is, in this example, every single term was what I call a pure term, meaning that the variable in 0.001x squared, there was just x's there, no y's. The last term was all y's, no x's. Places where things get a little bit trickier is when you have mixed terms, x's times y's. So we're going to do one more example of finding a partial derivative, and then it'll be your turn to take a look at some practice problems and also to take a look at remote assignment number 10. All right, so our last example, we're going to be going back to our Cobb-Douglas production function. And that was Q is equal to 30 times K to the 1/4 times L to the 3/4. Okay. And so our function Q, which is our quantity, or our production, is a function of two variables, K and L. So if I'm talking about partial derivatives, the partial derivatives that we want to calculate are the partial derivative of Q with respect to K and the partial derivative of Q with respect to L. And again, I can write partial derivative of Q with respect to K, or I can write it as Q subscript K. They both mean exactly the same thing. And dq over dl means the same thing as Q subscript L. Okay, so let's start with Q subscript K. So our subscript is the same letter that's in the denominator of this Leibniz notation. So K is the variable, is going to be our variable in this problem. And L is going to be a number. So I start by writing down the original function. Q is equal to 30 K to the 1/4 L to the 3/4. And what I noticed that's a little bit different about this example than the other two examples is, in our profit example, we had a bunch of terms added and subtracted together, and we analyzed each one separately. Here, we just have one term. There's no adding and subtracting. This is the one thing that we're going to take the derivative of. Okay, so our partial derivative with respect to K, which you can also write as dq over dk. So K is my variable, and this term has a K in it. So my process will be to copy down the numbers and take the derivative of K to the 1/4. So we have 30. So I copied down the 30. The derivative of K to the 1/4 will be 1/4 K. So I brought the number down in front. I subtract 1 from the power. 1/4 minus 1 is negative 3/4, which you can check on your calculator. So I have K to the negative 3/4. And then I carry along this L to the 3/4 number at the end. And so this is a legitimate final answer. I'm going to go ahead and clean up the 30 times 1/4. And I type that into my calculator, and what I get is 7.5. So I have 7.5 K to the negative 3/4 L to the positive 3/4. And so this is my partial derivative with respect to K. Okay. The other partial derivative is with respect to L. So we want to calculate the partial derivative with respect to L. So L is the variable, and now K is the number. My original function is Q is equal to 30 K to the 1/4 L to the 3/4. And so my partial derivative with respect to L, which you can also write as dq over dl with those funny partial d's. Okay, L is my variable. This is all one term multiplied together. So I'm going to carry along the numbers, the 30 and the k to the 1/4. So I have 30k to the 1/4. And now I'm going to take the derivative of L to the 3/4. So to take the derivative, I bring the 3/4 down in front. I subtract 1 from the power. And you can check in your calculator that 3/4 minus 1 is negative 1/4. So I have L to the negative 1/4. Okay, so I carried along the numbers. K is a number. And I take the derivative of the L to the 3/4. Final step is to clean up. So I have 30 times the 3/4, so I'll push the 3/4 to the front. And so 30 times 3/4, let me check what I wrote down. So I checked this ahead of time on my calculator. 30 times 3/4 is 22.5 K to the 1/4 L to the negative 1/4. And so this is my partial derivative of Q with respect to L. Okay, so your job after watching these videos is to get some practice calculating partial derivatives. Next class, we'll talk about how we apply these and how we use these partial derivatives to predict things about profit and cost and revenue. Okay, thanks for listening.